Hello everyone. Over this semester, Bo Yu, Yi Tao, Yi Yang, Ban Ruo, and I have been working on a project about beaconing detection using the neural structure learning model under the guidance of Yiwen Zhang, Emma Pan from KPMG, and Professor Jana from Columbia University. Our presentation will be structured in the following way. First, we will briefly introduce the definition of malwares and beaconing. After that, we will talk about the dataset we are using along with how we process the data. And then we will explain how we build the neural structure learning model and compare its performance with other baseline models. We will conclude our presentation by providing you with some results of our work and some potential improvements for future study. Let me begin by giving you some background of our project. In a world where data and internet are so ubiquitous and accessible, protecting your network against malware becomes one of the most pressing problems in cybersecurity. Malware are defined as any software intentionally designed to damage a computer, server, or computer network. Beaconing in particular is a type of malware that bypasses the firewall by reconnecting to an intermediate command and control server. Here we have a demonstration of the basic setup for beaconing. The state-of-art models for malware detection are not showing good performance in practice, and hence, our goal is to use neural structure learning for beaconing detection, and the workflow of how we approach our goal is as demonstrated.
For data contents, the summary of dataset is showing in the figure below on the right side. The dataset includes different attributes of NetFlow data, including categorical attributes like source and destination addresses, start time, protocol type, direction, etc., and numeric attributes like duration, total package, total bytes, etc. So the most important attributes for our capstone project are start time, source, and destination addresses. Besides the features in the given dataset, we also include two features indicating whether source and destination addresses are bogon. Labels of regular or beaconing are determined by the source address and destination address pairs. Start time, source addresses, destination addresses are used together to bin the data, which will be explained in the next following slides.
Next, I will talk about the data processing steps. First, we split the original dataset into training, validation, and test sets based on the source and destination address pairs. The proportions of training, validation, and test pairs are 20, 40, and 40 for both regular and beaconing pairs. As you can see in the figure below, we do the splits for regular and beaconing pairs separately, and then we put them together. Then we bin our data by a time window of 1 second. Data are put into bins based on their start time, source address, and destination address. The data binning procedure is shown in the figure on the right. We apply a min-max scaler on numerical features, and we do one-hot encoding on categorical features. In a time window of 1 second, the records with the same source address and destination address will be put together.
After putting data into corresponding time bins, there are two ways of feeding data into models. One approach is calculating the aggregate statistics, such as summation, averaging, counting, and others. As shown in the figure on the right, we calculate the aggregated statistics for each bin, which means one bin will be corresponded to one record of aggregated data. Then we put the aggregated data as the model input. If the model can process with the sequential data, the other approach is using the sequential data in each bin directly, which is demonstrated in the new figure on the right. And before feeding the data into a model, we need to trim and pad the data into a same sequence length. Besides the neural structured learning model, we also tried 3 other models for result comparison, where the logistic regression and artificial neural network models used the aggregated data as input. And on the other hand, the LSTM and NSL models use the sequential data as input. For the NSL model, in the model training stage, NSL applies the graph regularization to the base model, which can improve the model performance, where the base model can be various types of neural networks, like CNNs or RNNs. The base model we choose is LSTM, which can handle the sequential data as input. And as mentioned in the previous slide, we also tested an LSTM model without graph regularization to make comparison. The graph is generated by the training data using the following procedure. First, we flatten each bin sequential record into an 1D array. Then we calculate the similarities between the flattened records. And finally, to generate a graph, an edge is added when the similarity score between two records is above a threshold, and we then set the edge weight to the similarity score. And here is the pipeline for our NSL model. Highlights for these models are the graph generalization procedure, and we include a graph in the training stage, which is used to calculate the graph regularization.
As we can see right here, it is the results of our 4 different models. We use 4 different metrics to compare models: recall, precision, accuracy, and F1 score. You can see that the NSL model performed best in recall, accuracy, and F1 score. And also, the aggregated models, logistic regression and neural network, have a lower F1 score than the non-aggregated models, LSTM and NSL. We think it's possibly caused by the information loss when calculating the aggregation data. In addition, the NSL model has a better F1 score than the LSTM model, probably because of the introduction of graph structure during the training stage. For everything we've done right now, we have complete the major work of our project, but we still have a lot of space to improve in the future. For future improvement, the first thing is, as we know that the set of current data set is relatively small, so we need to find more data about beaconing analysis with the same data structure from open data source. For right now, we found a data set called CTU13. We can use more data from that data set. And also, we can try a better way to solve the class imbalance problem existing in our data set. Also, we need to find a better way to build the graph. The third thing is we need to optimize our model training time without hurting the performance, because we know that in real-life application, the training time is always very important. In the last, we need to reorganize our code so that it can automate the train and detect process. In the last, we want to say thank you to our mentors and the instructor.